So, good afternoon, everyone. Welcome to this webinar. Thank you for coming along. This afternoon, Julian, as a member of the EPCC staff, is going to share his top 10 or thereabouts tips for using HPC. So, over to you, Julian.
Thanks, Claire. Let me see if I can turn on my video. There we go. Cool. Well, thank you everyone for coming to this talk, where I'll be discussing the top 10 tips, more or less, that my colleagues at EPCC have said might be worth considering when using HPC facility. Now, as I look at the attendees list, I noticed that there are a fair few of my colleagues from EPCC on that list, so I'm kind of now worried that they've all shown up here to check that I have included the tips that they mentioned. I hope I have, but we shall see. So yeah, my name is Julian. I've been working at EPCC on the ARCHER2 program since it started, and yeah. Oh, well, thanks, Oliver. Here to heckle. Cool. So let's get started just straight away with these top 10-ish tips. The very first tip is probably it's one of the hardest ones when you're a researcher, especially early career researchers, I find tend to really struggle with this one, or really not consider this one, which is you shouldn't struggle alone. And this is true in general across the board, but especially for HPC. If you're on a HPC facility, there is always going to be an amount of support that you will have access to. So for a facility like ARCHER2, for instance, there's definitely the service desk that you can email with any questions that you might have. There are documentations that have been written that you can read. There are also there are a wide variety of places that you can go to for help and for advice. So as I said, ARCHER2 has a service desk, but so do most other HPC services that I've worked with. And if something isn't working, the job of those service desks is to help you. So do send in an email. We're here to help. We're here to help. The other place that you can go to if it's to do with an actual software development question that you're having is consider asking research software engineers about your research software. There are many RSE groups around the UK and I suspect worldwide. They might have different names. And I've put the link to one of them there. And then one final one that I've not actually included on this slide, but which can be very helpful is if you're using a software, a program that you have not coded up yourself, there's very likely going to be a community that uses that program. And that if that program is quite well used, say one of the bigger codes, the most used code on ARCHER2 at the moment is VAST, but it could be something like GROMACS, LAMPS, whatever. Any of those big research softwares packages, they will all have a community that uses them day in, day out, and are all happy to help answer questions. They'll also have the developers are usually keeping an eye on a specific community, a specific message board where you can ask questions, and also have the developers commenting and answering your questions. So you're not, sometimes when you're doing research, it might feel like you're by yourself, but that's really not the case. And do make use of the facilities that are there to help you. The next point is learn an in-terminal text editor. Now, this is very useful, we'll see later, because often when you're using a HPC facility, using anything that's got a visualizing part or a GUI can be quite expensive from a bandwidth point of view, which means that you'll either get huge amounts of lag or it just won't work. So using an inline text editor is really useful because it's much quicker to do. And if you just learn to use one, you'll be able to do a huge number of things on the HPC system without having to transfer files back to your local system, write them in your local GUI or text editor or whatever, and then send them back. Also, some text editors like Word will add like hidden symbols at the end of lines, which means that sometimes when you copy them across, your codes won't run as you'd expect them to. There's loads of little hidden issues that you get if you don't use an inline text editor, an in-terminal text editor. The three most common ones that I've heard of being used on general Linux systems, this isn't just HPC facilities, are Nano, which is a super simple program to use, and probably the one that a lot of people start with, but it doesn't have many functionalities. It's not very powerful as compared to the other two. The other two being Vim, which is a very powerful tool, and which is usually the default whenever you get onto a brand new system. Vim is there. So for instance, when we first got onto the ARCHER2 system to test it out, Vim was installed. The other two, Emacs and Nano, we had to install them, or someone from EPCC had to install them to make them available. And then the third one is Emacs, which is probably more intuitive to use than Vim, but and is almost always available. And it's one of those, there's such battle between people who say that you should use Vim versus people who say that you should use Emacs, that you'll usually get both everywhere. The big advantage of Emacs is probably that you can play a ton of games in there. There's a functionality which lets you play Tetris, it lets you play Pac-Man, it lets you play all those sorts of things. I'm pretty sure Vim doesn't do that. Other than that, I mean, I mainly use Vim because that's the one I grew up with, but I have heard some people mention that their views on Vim were maybe similar to their views on the bubonic plague. So there's quite a lot of resentment and discussion about which is better out of those two. But one of the next points, one of the advantages of large HPC facilities is that you have a ton of nodes to work with. You can run enormous jobs, bigger than anything you've run before, and that's definitely true for ARCHER2, for instance. But one of the problems with this is running jobs over a large number of nodes has a huge number of potential consequences, unexpected consequences. So for instance, your job that was working fine on your laptop or on maybe, let's call it 10 or 100 cores, once you start using 10,000 cores, you might notice that all of a sudden, well, it's creating one file per process per one file per core per variable you're outputting, and all of a sudden, because you've got a set number of files that you can have as well as a set amount of space you can have, you're reaching the limit, the cap of the number of files that you're able to create, and that causes your job to crash. So all of a sudden you need to think, well, how do I get that number down a bit? Other issues might be all of a sudden communication becomes an issue, and your job doesn't really work at that scale. And there's loads of other problems that might happen. And what we're saying here, the other one as well is like you've run your job on 10 cores or like on one node, and all of a sudden you write your script for like 100 nodes or 1,000 nodes, and there's a typo in your script. And so because it's running on such a large system, on such a large number of nodes, it won't make it through the queue for a number of hours or days. By the time it makes it through, it'll run for 10 seconds, it'll crash, and you'll be right where you started, looking for the typo. These are things that you can prevent by running a small test job. Just reduce the amount of time that your job will take to run, or even run it till it times out. That's absolutely fine. But run it for maybe just a minute on that large number of nodes, and check that there's nothing unforeseen, no problems that you didn't anticipate that happen. And that way, you might end up with something that blows up in your face, but at least it won't use up all of your compute time or waste your time, which is more valuable than compute in most of the cases, in all the cases, frankly. The next one is a similar point, which is run basic benchmarking. And this is true whether you're using a new program or whether you're running a new system in your program, you're using a program you know. You can run a very simple benchmark suite that'll cost you less than 100 node hours to work out exactly where your code will perform optimally. or your specific system will perform optimally. And you can use that information to save yourself thousands of node hours down the line. And this is definitely true of when you're running on hybrid systems. So I ran a couple of tests with GROMACS, which is a quite popular molecular dynamics code recently, where I was running this on Cirrus, which has CPUs and GPUs. But I kind of wanted to check whether there was a sweet spot. GROMACS has kind of three numbers that you can play around with when running on these sorts of systems. It's hybrid OpenMP MPI code, and it also makes use of GPUs. So the three numbers you can play with is how many GPUs are you using, how many MPI processes, and how many OpenMP threads per process are you using. And I found out that I was looking at two systems, one of which had 1.4 thousand atoms, and the other one of which had about 1.4 million atoms, and the other one of which had 2 million atoms. Quite close, right? You'd expect them both to sort of be optimal at the same point, but it turned out that that really wasn't the case. One of them worked much better with a certain number of OpenMP threads, whereas the other one worked much better on a different number of OpenMP threads. So even that simple test could reduce my runtime significantly. When you're considering a benchmark, what you're trying to do is you're wanting to take the system you want to run, and you just want to run it for a very short amount of time, something that'll run in order tens of seconds, if not maybe minutes at a push. And just run a baseline at whatever you think is sensible, and then double that and half that, and check whether it's still check whether your initial one is still the fastest. And if not, you can use the new point you can then double the point that was faster or halve it, depending on which direction it was. And very quickly, you'll get to your optimum. A lot of the more popular HPC programs and softwares will have benchmarking data out there. So for instance, talking about GROMACS again, I'm aware that there's a GROMACS best practice guide, which contains a cookbook that helps define, that helps you find out what a correct number, where a system will run optimally on a certain number of GPUs, CPUs, that sort of thing. So looking for those benchmarks can be really useful, but you still want to spend the time to test your system specifically, because there might be some discrepancies. And definitely if you're using a new architecture, or if you're running on a new system, if you've just swapped everything over from one system to another, you also should run a couple of benchmarks, because in the long run, it can save you a ton of compute time. Plan for the future, because it'll be here sooner than you think. And this covers a huge amount of things. The first one is data. Imagine that everything goes wrong with your data on the HPC facility. You don't want that to mean that you've lost it all. So all of a sudden you need to think, this covers backing up your data. When backing up your data, things that you might want to consider are things like, well, which parts of your data are worth backing up? Not all data is created the same. That part of the data, how do you want to back it up? Where do you want to back it up to? How are you going to transfer it from the HPC facility to the backup facility? Will compressing your data help or hinder that transfer process? Compression can mean that you're transferring less data, but there's a cost to compression. It takes time to compress a huge number of files. And if the time that you save on data transfer is lost and then some when you're zipping your files or compressing your files, then it's not really worth compressing your files. You also want to consider, if you're transferring a large number of files, you want to consider making sure that you archive them, put them all together in one file, either a zip file or a tar archive, a tape archive, in order to ensure that you lose some of that overhead. For every single file that you transfer using most of the transfer protocols, there's an overhead. And if you're able to reduce that by only transferring one meta file that contains everything you've got, you reduce that overhead substantially if you have a large number of files, and your transfer will go faster. But thinking about all of these things before generating the data is usually a better way to approach this problem than to have all of your data already there and think, well, how am I going to transfer it now? Now, for less data focused things, when you're writing code for use on a HPC facility, think carefully before you limit your code. And that can be limits like, let's say, for instance, you are, you're trying to make a program which solves something in, which is looking at a three-dimensional, solving three-dimensional physics of some sort of other. Let's take a molecular dynamics program. And you're considering how to decompose space, so how to split the work amongst the processors. Well, it might be easiest to start off by thinking about splitting everything in one dimension, or maybe two dimensions, but further down the line, you might begin to notice that actually the time that you gained by doing this quick fix of taking the simplest solution at the very start, to then fix your code when it's nearly all done, or all done and has been working for a while, but you notice that there's always this recurring bug, might take much more. If at the start you'd considered, well, how do I make sure that this works appropriately? How do I make sure that? And the last point about planning for the future is be considerate of future collaborators. When I started my PhD, I inherited a code. I'm sure we all have a story like this. And the person who'd written the code had decided to name all of their dummy variables after biblical characters. And it was a pain to try to understand what was going on between all the Isaiahs and the Thomases and what they were doing. So think of your future collaborators. Make sure that your code is easy to read for whoever ends up picking it up. Cool. So many of you will laugh that it's taken me 5 points before I got to reading the documentations, but please do read the docs. Most HPC facilities provide good documentations, and I know this for a couple of reasons. The first one is I helped write some of them for Cirrus and ARCHER2, which is maybe not a good sign, by the way. But when we start to write them, we often look at what other HPC facilities have in their documentations to get an idea of what they do well and to help improve our documentations. So I know that. So I know that most HPC facilities in the UK, or at least the ones that we were looking into, they have very good documentations. The other reason you might want to read the documentations is, how I said earlier, if you have any problems, you can contact a service desk for the HPC facility you're using. When a service desk gets a query, the first thing they'll do is check the documentations to check that it's not answered there. And if it is, they'll send you the link and say, this is what it says in the docs, which is really helpful because it solves your problem, but it also shows that that it was written there already. So you can save yourself the weight of getting an email back from the service desk by checking the documentations. And finally, this is a quick pointer about documentations. A lot of the HPC facilities are starting to use documentations that are accessible and improvable by users. So if at any point you either spot a mistake in the documentations for the ARCHER2 docs, say for instance, because I put the link to that one, or if you think that something should be there that isn't there, you're more than welcome to add it and it will be reviewed. And if the ARCHER2 support team agrees with the changes you're proposing, the documentations will be updated to include that, making the docs more useful for everyone. But yes, read the docs is an important number 6. The 7th point is make use of the available training courses. Lots of HPC software, data analysis, training materials are available as courses. The ARCHER2 program that I work with, they have a ton of training courses. I think that at the moment, they're like, as we speak, there's an introduction to Fortran programming course happening, though that might have finished recently, maybe, as in the past couple of minutes. All of the courses that are run on the ARCHER2 program, they are kept in the course repository, where you can find, for every single course, you can find the course material, which is usually a easy to read through, work as you go type of course material, along with a video of the video recording of the course being presented by the presenter. Other sources are the Carpentries. On carpentries.org, they have a ton of various courses, and also Code Refinery has a number of courses available there. Other places might be, you can also find a ton of resources on YouTube. Usually has for software packages, will have a large number of videos, and in a lot of other places that I've probably missed here. Number 8 is learn Linux command line. Just to be able to log on to a HPC facility, you'll probably be using SSH. When you use SSH, you end up on the facility and all you have is a Linux command line. You'll very quickly have to learn the simple commands like ls to list, cd to change directory, make dir to make a directory, that sort of thing. But learning that is important. However, once you've learned all of the basic knowledge that you need to just move around as you want within your directories on the HPC facility, I would recommend that you take a bit more time to learn some of the more advanced commands that are available, because you'll find that they're very useful. They can be very powerful. They are very useful. Things like sed, for instance, to replace words in a document, awk to print certain parts of a document, paste. UUID gen is excellent for making random 128 character sequences. And it's possible to combine Bash and Python to get some really powerful capabilities. One note I want to make on this slide is I mainly picked this for the illustration for the picture. I've not read the book, as it were, but apparently it's getting amazing reviews on Amazon, so do check it out. It might be an excellent book, and let me know if it is. Number 9 is don't reinvent the wheel. There are a ton of functionalities out there that are already present and usable from within libraries. Like libraries like fast Fourier transforms. You can use FFTW for fast Fourier transforms. A lot of things can be found in BLAST, LAPACK, ScalaPack. You can also use pestering is excellent for speeding some things up. Instead of reinventing the wheel, instead of writing your own bit of code that does fast Fourier transforms, let's say, do use the available quick libraries from FFTW. For one, they'll be quicker. Unless you're developing FFTW or developing for FFTW, for like your own FFTW libraries, or if you're paid by someone to develop quicker FFTW functions, there is no doubt that what's available in those libraries will be faster than what you're able to make. Also, it saves you time. Like, you don't need to spend time trying to get this to work because it's already written. You just need to link to it. But HPC facilities will often come with optimized libraries. So for instance, on ARCHER2, Cray provides the Cray libsci package, which has all of the Cray developed or HPE developed maths libraries like BLAS and LAPACK available. They also provide the Cray FFTW module, which gives you access to the HPE developed FFTW libraries. And they've been developed with ARCHER2 in mind, or with the system architecture of ARCHER2 in mind. So you're going to be able to get a lot out of that code. So make use of it. And likewise, a lot of compilers have their own optimized libraries as well that you can use. So for instance, Intel has Intel MKL and things like that. Make use of those where possible. The other one as well is there is always a large amount of centrally maintained software on HPC facilities. So for instance, I think on ARCHER2 we maintain, I think it's 27 different scientific software, and all of those have their own module. In a lot of cases, in fact, in most cases, the team that built those will have tested various conditions to try to get the most optimized version of that scientific software so that it goes as fast as possible. If you can, use the centrally installed module. If you can't, we've always made our installation instructions available, so you can ask for those. We'll be happy to provide them. Use those as a basis to then add your things, because you will probably get a noticeable performance improvement by doing this. And now the final point is much more geared towards science, people using HPC for scientific reasons. And that's consider learning something like Pandas or R. Yeah, both of those are fantastic tools for manipulating data. And because of the amount of data that you'll be generating on a HPC facility, having a quick way of extracting the bit that you care about, the bit that you want to plot, the bit that you probably want to back up, is very useful. And Pandas is the Python implementation of this, which can be parallelized using Dask, is very easy to learn. And likewise, R is quite a well-known tool. In fact, we've got a couple of, I'm certain that we've got a couple of courses in the ARCHER2 training about using R. But yes, do consider learning something to look through your data, to manipulate your data, and to extract the important data from your simulations, because you can gain a lot from doing this. Now, I don't think I mentioned this at the start, but in order to collate this list, what I did is I went around and asked my EPCC colleagues whether they had any suggestions for this. This talk is very heavily, well, I used as a framework a talk that was previously given by one of my colleagues, Andy Turner, who in turn also used as a framework a previous talk given by one of our colleagues, Nick Brown. So there's a fair few of their points in there, but I got a few other points as well when just generally chatting and asking around the office. Some of them unfortunately did not make the cut, so I've added them here as a quick number 11. And so let's quickly go through those. Understand your black boxes. I've met so many people who run a simulation, and when you ask them, well, okay, what does the simulation do? They'll say, I don't know. I put the answers in at one end and I get the answers out at the other end. Don't do that. Make sure you understand what you're running. Next one is sudo will not solve anything on a HPC facility. In fact, in most cases, sudo is disabled and will send an email to the systems team, who will then send you an email asking why you used that command, because you really shouldn't. So a number of online instructions kind of say, oh, well, just do this steps, and one of the steps says, and now you run sudo whatever. That's not going to work. Think before running things through Python. So I think my best example for this is I once was talking to someone who was running something in Python, and they'd gotten an error message. And what they were running is they were running Quantum Espresso through lamps through Python, and they had no idea where the problem was originating. Quantum Espresso works perfectly fine on its own. Quantum Espresso works perfectly fine when you run it through lamps. Lamps works perfectly fine on its own. There's no need to add that extra Python step. but they were really keen on running everything through Python because that's the language that they understood, and that led to a huge number of complications. Don't just go through Python because Python's the thing you know. Make sure that it'll actually add something before using it. Consider visualizing things locally. I've hinted at this before, but there is a limited bandwidth to reaching the HPC facility. And every command that you send, when you're working locally, every command that you submit to the HPC facility needs to get there, usually via the internet. And every reply that you get from that command, every output command, is also brought back to you via the internet. If you're trying to run a GUI on a HPC facility, that is a ton of data that is being streamed. And that'll do one of two things. Either it'll reduce the available bandwidth for everyone else, or what most likely will happen is it'll be super slow for you. That'll cause lag, it'll be really frustrating. Where possible, transfer the things you want to visualize locally and then visualize them there rather than on the HPC facility. The next one is don't underestimate the cost of reading and writing. When you're reading super large files, this can be quite costly. There's ways that you can mitigate this cost, but you should consider them before you just submit your job to the compute nodes. Because you might have a ton of compute nodes that are sitting around waiting for just a file to be read. Think about that before you submit those jobs for larger files. Likewise, when you're writing large files, make sure that you consider how things are being written and whether they're being written optimally. And finally, this is more aimed at anyone who does who is altering codes or doing programming. Make sure that you know the consequences of the code that you're about to change when you're making that change. So for instance, don't just change something in a code if you don't understand what it does. And this is kind of linked to the black box statement, but at least make sure you understand what you're changing before you make any changes to it. Cool. So with that, that is the end of the 10-ish tips. I've put them there as a reminder. I'm sure there's a ton that I've forgotten. Hopefully my colleagues at EPCC won't now bombard me with all of the tips that I should have added and forgot to include. But please do let me know if there's any you feel I should have added, and please let me know if you have any questions about any of these tips or anything else I might be able to answer them. Otherwise, thank you very much for attending this talk.
Many thanks, Julian.